All right, welcome back, Calcsters. Today, we get an awesome new topic, and it kind of relates to our bell ringer. Recall the bell ringer, we had a function that we just could not solve for y, or wasn't worth the time to solve for y. Now, that's going to happen a lot. The real world is not nice and neat in y equals type form all the time, even when you collect all your data. So it means we need a way to deal with that situation. So in 3.2, it is hate that 3. In 3.2, it is exactly that, where we're going to get a new word that I don't think we've ever seen. Not in math anyway. 3.2, it'll take us a couple days at least, but our focus is going to be on the idea of what is called implicit differentiation. Now, you guys maybe have seen and used the word implicit before. Do you have an idea of what implicit means? So not explicitly said. So for example, if we had a quiz tomorrow, we don't, just for the record, but I could explicitly tell you there is a quiz tomorrow. And that is like defining it right then and there. Or more commonly, and I really do typically do that, but the other way that I approach it is, hey guys, we're at the middle of the chapter. And without saying it, you guys know what the implication is, right? You know what I'm implying, my implicit message. Okay, so with that, we have two different ways we can write things. So right off the bat, we just want to be able to identify two different situations. So we're going to identify explicit and implicit. And I'm going to say explicitly and implicitly defined functions. Okay, it is really pretty easy to see which one is defined explicit or not. And it turns out really just one thing we need to check. So we'll go ahead and I'm not going to say explicitly defined here, but we'll just say explicit. Now, not profanity. That is the other way that explicit shows up, explicit lyrics. Fun fact, two things kept me awake last night. One was the thing that I've referenced several times. The second was a question that I had for you guys, which I'm still mortified about. And thank my lucky stars, it was not. Okay. Cool. Told all the other classes about it, didn't use the language. And did anybody ask anybody in here? Yeah, terrible. All right. Anyway, here we go. Explicit, super easy. It just means it is solved for a variable. Now, normally, what is a variable that we have a function solved for? We don't normally solve it for x. We don't write x equals. Typically y. Now, it doesn't really matter what it is, but in our typically y. In our math system and just the system that we do math in globally, normally this is what we've seen every time until today, with one small exception. Can anybody think of any situation where we had an equation that we graphed that wasn't just solved for y? What is this? It's a circle. Okay, this thing, you could solve it for y, but we typically don't, right? This thing is an implicit function right now, and whether or not it's really a function, we'd have to dig into it. But I just want to highlight, you've seen this at least one time. Now, in contrast with that, we have implicit, which if explicit means it was solved for the variable, use your superpowers of deduction. What do you think implicit functions are? Not solved for variable. And just to be clear, VAR, the reason that I use this is because on your calculators, it's short for variable. Okay, so now two ways that you can really pick this out, and two really common things that happen. Either the x and the y, x and y, are stuck together, typically through either exponentiation or multiplication or division, something, but they're going to be stuck together somehow. Or alternatively, and this isn't really an additional thing, this is like the telltale sign, but more so, not all functions can be solved for y nicely. Not all func can be nicely solved. Okay. Now, we get to a point where we either have two options. We either have to do the 20 or 30 or 40 or 50 minutes of work for simple, quote unquote, problems to be able to really solve it for y, or we just look at it as it's defined implicitly and say, okay, let's try to take the derivative now. Now, that seems like it's going to be crazy, and it's strange the first couple times, but we're going to do it, and hopefully we'll all agree that it's not terrible. So here's what I want to do. For the following, just to get practice, before we do any calc, I want us to write the implicit and the explicit, and I'm going to put a parenthesis here to say if possible, for each. And we'll just look at it. Okay, so we're going to see one of these right off the bat, or here in a moment, that looks as something similar to what we've dealt with. Here we go. On A, I want to write, given the following, x over y equals 4. Now, one of our answers might already be here, and there's not a good way to separate it. Is this thing right now, is it solved for a variable? Not yet. Are my x's and y's stuck together somehow? So this is going to be weird, but rather than making us rewrite it, what is this form right now then? Is this an implicitly defined function or an explicitly defined function? This is implicit. My x's and y's are stuck together on the same side. Now, this is very different than the bell ringer. This is the implicit version of this function. Is it possible to find for this function the explicit version? Now, that question, if it doesn't quite, if you're not sure right away, I'm getting some nods. Just to check, what is it? Y equals x over 4. Now, we multiplied by y, we divided by 4, we just solved it. Now, if this problem presents itself, was that a wild amount of work to get to y equals? So I'd probably just do this one. I would take the 30 seconds, I would write it as y equals, and I would differentiate it. Nothing crazy to it. What's the constant multiple on our explicit version? 1/4. That's 1/4 x. So the 1/4 would come out, and it's just 1/4 is a derivative. Okay, no chain rule, no nothing. Nothing too crazy there, I don't think. On B, I want you guys to do the same thing for me. These all work out weird because I have to either give you the implicit or the explicit version. So we'll just do it like we did the last one. Let's say I have x squared plus y squared equals 9. Is this one right now a function defined implicitly or explicitly? Implicit. Now, they're not stuck together by multiplication or anything, but x's and y's are on the same side, right? They're stuck together, quote unquote, by addition this time. Additionally, though, it's not solved for y yet. Now, this is the implicit version. I'm fine with that. I want you guys to get a little algebra practice. I want you to solve this for the explicit version. And it turns out maybe there's two pieces, just maybe. I'll give you a second. I'm only going to write one piece, but I want you guys to take this implicitly defined function and write me the explicit rule. I'll give you guys just a moment. If we want to rearrange this one, and we're just going to, we're going to work it together. We're going to do it step by step real quick. Help me out. I want to rearrange. What are we solving for? Okay, so step one, anybody have objections to me saying it's this? Okay, now if I want y instead of y squared, which it's weird, but it's still implicitly defined here because we haven't solved it for y, I'm going to take the square root. I'll do the left side, it's y. What's the right side square root? So careful, does it work? Can we split it up? Like if I know the square root of 13 can be written as 9 plus 4, it's definitely not 5. We cannot take the square root. We can't do it. We can't with a subtraction or a sum. What has to go in front of this? Boom. Now we have it explicitly defined. Several people avoid the mistake. You cannot take the square root of a sum or difference. That's my counterexample, just to show it. Cool. Now that we have it, there's two pieces to this, and each of them are defined how? Explicitly. You're lucky I didn't call on you, Miss Janae. I thought about calling on you. All right. Now, yeah, 7. All right. I suggested a Halloween costume to a couple of your Raider underclassmen. I'm not going to tell you what it is unless I see that they don't commit to it, but it's awesome. It's not me. I would do it if I didn't already have a creeper mask. It is 6'7". 100%. I am not. No. We get that Friday off. You get Thursday and. Yep. No school Halloween, which is awesome. All right. Now, in contrast, we're obviously not going to try to work through this one, but if I do something like the following, the natural log of xy times e to the x squared plus y squared equals x root y. Is this thing defined implicitly or explicitly? It's defined implicit, right? They're all mixed together. Do you want to find the explicit version of this function? Me neither. I'm not even convinced that I can, but I'm going to be honest. I don't really care if I can or not, because even if I could, the amount of work that it would take is not worth it for me. So we'll just say, check this one, implicit right off the bat. That's fine and dandy. If we want the explicit version, nah, just that. Just nope. Not going to even try. Not even worried about it. Bruh. Cool. All right. Now, here's the deal. I don't want to do it. If we had just enough grit and perseverance and a crazy amount of time, or we had somebody smarter or better at algebra than any of us, could this theoretically, like we all agree that somebody probably can solve this for y? That is our get through. I don't know how to do it. I haven't played around with this problem. I just made it up off the top of my head. Somebody probably could. I don't know if that somebody is me, but somebody could. And if we can all agree that, well, I can't, but somebody could, then we have everything that we need to start differentiating. So here's the cool thing. From this, it turns out that in the situation where it's easy to find the explicit, I would encourage, let's just do it. Like, just take the little bit of time to rewrite it as an explicit, and then we could deal with it. In certain situations, like this, and many that are even easier than this, we don't want to have to find that explicit version, which brings us directly in to this. And I know it's a repeat, but let's actually dig in to not just how we define these functions, but look at what's called implicit differentiation. Okay, we are all relying on the fact that somebody could solve whatever it is that we're looking at for y. Okay, so right off the bat, we're not going to really do anything crazy, except we're going to use very specific notation. Now, your book is going to suggest we can use one of like a couple different notations. I am going to use ddx throughout these problems. ddx, which means the derivative with respect to x. So check it out. We haven't really viewed it like this. We're just going to jump in with examples immediately. So several examples, we'll get a feel for it, and then we'll switch notation here in a couple minutes. So I'm just going to say differentiate, or just ddx if you'd rather. So for our first one, I want to find dy dx, so the derivative of y with respect to x, of, and let's do it for x squared, and I'm not going to do it like that. I'm going to write of for, we'll see why, x squared plus y squared equals 4. Now, here's where we're going to see something new. If I have an equation here, right? Could I add 5 to the left side? Is that allowed? If we add 5 to the other side, it's allowed, right? If I do, could I square this side? as long as I squared this side. Could I take the square root? It won't simplify, but as long as I do the same thing to both sides, I'm okay, right? Now, we've been using an operation the whole time, but we never really wrote it. You do not have to write this. I just want to show you with this simpler example. If I said find y given this, could you find me the derivative? Now, we've always just jumped to just right away y prime, right? But check this out. With the understanding that we just write y prime, if I do this operation, saying take the derivative on the left, if I want my algebra to work, what else must I do? I must also do it on the right side. Like, it's that same property, right? It's just adding, subtracting, taking the natural log, the square root. As long as we do it to both sides, we're okay. Now, everywhere up until now, we haven't had to do this because we know that the derivative of y with respect to x, we simply write y prime. But we've really and truly been taking the derivative of the left side to get y prime, and then we take the derivative of the right side as 2x. Everybody cool with that idea? I don't think we've ever seen it like that, but you've been doing it. We just never had to talk about it. Okay, the same thing is going to happen here. I want to take the derivative of each side with respect to what? X. Now, for this first problem, you're going to write like more than we normally will, but let's just jump in. I'm going to leave just enough room that I can take the derivative with respect to x of the left side. So I'm just going to rewrite the entire left side with a bracket around it. So here we go, x squared plus y squared. And then I'm going to take the derivative with respect to x. Now, the same thing is going to happen. If I take the derivative of the left side of this equation, then we better take the derivative of the right side of this equation as well. Now, we don't go through the process of defining this as a property of equality, but it is. Whether it's a natural log, a square root, the same idea applies. So now we just need to keep kicking. And here's the weirdest part. What's the derivative of a sum? The sum of the derivatives. Everybody cool with that? Okay. Now, when I do that, and I'm going to split this up, and this is going to be the ugliest problem that we do for quite a while. And I promise we won't show as much work ever again on these, but I want to make sure we hit every little piece. You guys said the derivative of a sum is just a sum of the derivatives. Do you agree this is the first one? Plus the derivative with respect to x of this one. Now, on this other side, I'm just going to write the derivative. What is the derivative? 0. Okay, huge important note, because I'm going to check. We're not going to write anything down yet. What's the derivative of this? 2x. I agree. What's the derivative of this? I disagree. Now, there's a reason that I disagree. You're just not entirely right. You're not entirely wrong, but you're not entirely right. As I look at this, could this be solved for y? Absolutely. Which means, is there a world, and we just don't see it, but is there an expression where y equals something in terms of x? So like, I know it's really going to be 4 minus x squared, and it's going to be plus or minus, but if we didn't know that, is y eventually, could it be an expression in terms of x? I might be losing you guys, I can't tell. The blank faces make me think so. Could you solve this for y? So I don't want you to write this down, but I do want to make sure that we have it. I'm going to write it on the board so it shows. And we're going to make a comment here. Now, for this, note rather, y is an expression in terms of x. Now, I don't really care what it is, but it's doable to see it in this one. Very specifically, if we went through this whole process, don't write in pink, I just want to think about it. We could find that y is equal to plus or minus the square root of 4 minus x squared. If I put that in here, this expression then, and I'm not going to put it in, I'm just trying to make sure we can connect this piece. Do you agree that this d dx of y squared could then be this? 4 minus x squared to the 1/2 squared. Is that still y squared? Now, the fact that we can find it and actually write it down is convenient to us, but I don't want to have to go through all this process. if I understand that y is an expression in terms of x, just like u of x was when we did our chain rule, then we see maybe that there's a chain rule needed, right? Now, instead of writing this, we're just going to write what variable instead of 4 minus x squared to the 1/2. It's just a y. And here's the last little piece that's going to help us avoid mistakes. I'm taking the derivative d with respect to what? X. If you just try to use 2y, there's no x in here. You can't do the derivative of this thing without implicitly assuming it can be solved. If you just wanted it to be 2y, it'd have to be d dy here. Okay, that idea is strange. There is a chain rule required for this. So just like we did with u, help me out with the chain rule. If instead of y, and I again don't have to write it, but if I said what is the derivative of this, where u is an expression of x, could we chain rule it? It'd be 2u times what? U prime. So check it out. We're going to use that to our advantage. If you didn't catch that, this would be 2u times u prime, just u of x squared, which means let's differentiate anything and everything that we can. This one's derivative, you guys already told me, was what? 2x plus, now this one's going to be ugly, but it's a chain rule. It's 2y times y prime, or if you'd rather, and I'm going to write it this way specifically, dy dx. JJ suggested y prime. I agree, but I just want to write dy dx for now. Okay, still all equal to what? 0. And I just really want to stress, why did I write this one out like this again? It's a chain rule. That's it. It's chain rule. It's no different than if we had u. We just happen to have a y now because that's commonly what we use. Okay, at this point in time, I'm feeling pretty good about this. What are we actually trying to find in this problem? So in our directions, we stated find what? Dy dx. What did we just get into our problem? Here's what I want you to do. We'll meet up in a second. I want you to take this last expression that we just wrote, and we're trying to solve it for dy dx, right? Solve it for dy dx. Treat it like it's just a variable. Shortly, we'll start using y prime instead. Dy dx is what I want you to solve for. I'll give you a moment. I'll pause it, and we'll come back together. Here we go. As we go through, any objections to me just subtracting 2x? So if I take little steps, 2y dy dx, and we can do times if you want us to put it, or if you want me to put it, that's weird, equals negative 2x. Everybody okay with that first step? Now, if I'm solving for dy dx, what do you want me to divide by now? By 2y, which means we get dy dx equals negative 2x over 2y. And then one more step, is there any obvious simplification that we should all endorse? So the 2's divide out, and we wind up with dy dx is exactly negative x over y. Now, couple things about this. When we look at this, all of a sudden, we change just a little bit. If I want to know the slope of a tangent line, which is still what we're after, instead of just giving me an x, I now need which variables? I need x and y. I need a whole ordered pair, and that's okay. If I know what x is, and we'll see this in future problems, but if I know what x is, could I find y? So for example, if x is 0, and here's my original, I'm just covering up the d dx. If I wanted to know the slope of the tangent line when x is 0, well, let's just do a little scratch work. 0 plus y squared equals 4, y would have to be what? If we just had y squared equals 4. So I'd get 0, 2 would be one of them, and 0, negative 2 for my plus or minus. All we see here is a shape that is not like, doesn't pass the vertical line test when we run it alone, but instead of splitting it up into two different functions, we're just doing it all together and saying, well, let's figure out what y values we would have to choose. Now, if that doesn't mean a ton to you just right now as we're talking through it, that's okay. For this first example, I had JJ suggest something a few minutes ago that I'm pretty sure I highlighted then. Dy dx is not the standard for notation, right? Normally, what do we use? Normally, and I'm going to make this note, this first time it's nice to see that if I just did d dx to each side, and what we do, normally we don't use dy dx though. Normally, we use y prime instead of dy dx. Okay, now if you prefer the dy dx, you can do it. Like, I'm fine with that. We're going to start one more. We probably won't finish it in class, but I'm going to give you a 1-question homework assignment. And it's going to be try to finish this. So one more. Let's see here. I'll just start up on the next page. I didn't start at the beginning either for some reason. So example B. I want us to find y prime given the wonderful implicitly defined function, the sine of xy equals 2x. Now, the only, not maybe the only, but the major benefit to dy dx is it tells me very clearly that I'm differentiating with respect to x. If we just write y prime, it is assumed that we're talking dy dx here. Okay, should we start this together? Okay, if I want dy dx, 2 options. Either I can try to deal with the arc sine, which if I do that, we can get the answer. But real quick, what is the derivative of arc sine? Let's not do that then, right? Like, we don't have it, so we won't use it. So I want to find dy dx. What should I do to each side immediately? How did we start our last problem if we're looking for a derivative? Take the derivative, right? So we didn't solve for y, Sean, just to be really clear. We did not solve for y. Last time, we'd never once solved for y. We just started differentiating. Let's do that unless you want to solve it for y. But we don't, because we don't know the derivative. So here we go. D dx on the left of, looks like sine xy. And that is equal to the d dx on the right side. We'll do the same thing to both of, I think I did a lighter blue. Nope, 2x. Okay, I will do the left, and then I'll leave the right side for you. What's it? It's 2. Okay, I'm done. You guys get to do the derivative of the other side, and realistically, we're going to start. Okay, we have 30 seconds to start this problem. Is there a clear outside and inside? What's the outside function? And what's its derivative? Cosine. So we take cosine of, what do we do with the inside? Keep it the same, xy. Now we're going to take the derivative now, d dx, of what? Xy. What rule are you going to have to use for the derivative of xy? Let me rephrase this. What rule are you going to use for the derivative of x times y? It's a product rule. Okay, use a product rule. When you do the derivative of the second, it is just y prime. Like, we don't know what it is. It's y prime. Cool. Finish this tonight. I'm going to put it in the grade book, and I'm going to do it right now so I don't forget. 1-point homework assignment. Finish it. Try it. Cool.